Today's lesson is 11.7 geometric probability. Now, geometric probability is basically commonly noted with questions of find the probability that if say a dart lands somewhere in the area of this larger shape, what's the chance it'll land in a shaded area, possibly another shape inside of it. And so we'll deal with that a little bit, and we'll also deal with some probability in length. So starting off with the length version. Let AB be a segment that contains a segment CD. If point K on AB is chosen at random, then the probability that it is on CD is the ratio of the length of CD to the length of AB. Now, in general, probability is typically chance probability of event equals the number of ways event can happen over total number of events, right? Total number of ways, right? Now, same idea here. It'd be total length of AB for our total number of ways, and our chance of something happening would be the total distance of CD over total distance of AB, right? And geometric probability, again, just a little term here, is a ratio involving geometric measures such as length and area. So we'll start out with one example of this, and the rest will be area ones. Find the probability that a point chosen at randomly on PQ is on the given segment. Express the answer as a fraction, decimal, and a percent. Now, notice it says on PQ. So don't just start thinking, oh, 6 minus negative 6, that's 12. But PQ is 5 to negative 5. So our first math is going to be 5 minus negative 5 equals 10. Now, normally they would put this in absolute value, but since I see the picture, we're going to start with the largest value, which is Q, subtract P, and that gets you the distance of PQ. Right? And so we get the distance is 10 of this segment. So RT is going to be, okay, what is the distance from negative 1 to negative 2? That's 1. I don't believe I showed that math, but that's pretty simple. That's 1 over 10, right? Because RT is 1, PQ is 10, so 1 to 10, and then that's our fraction for our answer. Decimal would be 0.1, percent would be 10%, right? Move the decimals twice to get your percent, and there it is. Next, PS, which I already unveiled. PS here is 9, 4 minus negative 5, right? Distance, I believe, was chapter 1 when we did this type of distance. So if you need a review on that, you can look back at chapter 1, and I can probably reference a lesson on Google Classroom. 4 minus negative 5 is 9. So we're going to have 9 over 10 this time, which is 0.9 and 90%. Again, 9 divided by 10 gives you 0.9. Multiply this by 100 and then give it a percent sign, right? Percent per 100, right? TS. Now, T to S is 4 minus negative 1. Looks like we're covering 1, 2, 3, 4, 5. Mathematically, that would be how we would do that. 5 over 10 is 1/2. We can simplify, which is still 0.5, and that is 50%. Lastly, R cubed, negative 2 to 5 is going to be 7. 5 minus a negative 2. 7 over 10 equals 0.7 and 70%. Probability in area is going to be, let's say, probability chance that K is in region M is going to be area of M over area of the whole, which in this case is J. Okay, all right, so this is the same idea as last time. Let J be a region that contains region M. If point K is in J is chosen at random, then what's the probability, right? The probability that it is in region M is the ratio of area M to the area of J. For example, it starts off pretty big. Find the probability that a randomly chosen point in the figure, talking the whole figure, lies in the shaded region. So in this case, we've got a rectangle, right? It's kind of see what it looks like, right? Most of the time in geometry, I need to tell it to you, but in this case, see what it looks like. In this case, we have a rectangle, and it looks like we have 6 congruent circles in here, and that's what they are. They're all equal circles. So we've got 12 foot for width. Now we need to find the length. Now, how would we find this in the first place, right? I like to set up the probability kind of that we're going to solve right away. So notice the area is not the circles, right? So what we're going to do is we're going to do area of the whole rectangle minus 6 times the area of circles, because there are 6 circles, 1, 2, 3, 4, 5, 6. So 6 minus the area of one circle would give us the numerator, that the whole is the area of the rectangle. So we're going to need area of the rectangle and area of the circle. Now in this case, we've got width is 12, but how many radii is width? We've got 1, 2, 3, 4 radii, right? Because radii down, radii up, 2 for this circle. Radii down, radii up, 2 for this circle, and they're both equal. So 12 divided by 4r, or 4r is 12, r is 3. So all these circles have radius 3, and now we can also figure out 1, 2, 3, 4, 5, 6 radiuses going left to right. So 6 times 3 will give us 18 feet for our length. And now we can find the area of the whole pretty easily. And we can also find area of each circle. So area of the circle is pi r squared. R is 3, so pi times 3 squared is 9 pi is the area of one circle. Area of the rectangle is 12 times 18, length times width, and that is 216. And now plugging it in basically back here. 216 minus 6 times 9 pi, because it was 6 circles, all over 216, to get 0.2146. Now in general, I like to round to the second decimal. However, because decimals were already going to be, actually we're always going to be less than 1. Right? It can't be 110% to land somewhere, right? So I like to round to the third decimal. So 2146, round up to 215. So 0.215 is the chance, 21.5%. Next, we've got a circle that looks like it was fully shaded until there was a blank circle of radius 8 on top and another circle of radius half of 5, small, I call it small circle, and then a triangle which is base 7, height 8.5. Now this was intended to be from left to right. We've got 8 radius, another 8, and 7 giving us the diameter of this circle. And just for problem solving, again, we're solving for shaded area, so area of the whole minus these 3 areas, area medium, area small, area triangle, and I think I call them MO, LO, SO for like large circle, area of the whole, which is large circle, minus area of the medium circle, radius 8, minus area of the small circle, radius 2.5, minus area of the triangle, all over area of a large circle. Okay, so 8 plus 8 plus 7 gives us the diameter of the whole, which is not an even number, unfortunately. 23 over 2, which is going to be about 11.5, is our radius of the large circle. Now, doing these one at a time here, we've got area of the large circle, since we just found this out, is pi r squared, 11.5 squared, to get 132.25 pi. Now, why do I leave it like this? If I round this answer, and then I round my next circle, and round my next circle, and then maybe this triangle is actually a nice number, I've rounded 1, 2, 3 times, and then when I do my probability, probably going to round a 4th time, and that's not minimizing our rounding. My goal is to minimize at most twice, if I have to. In this case, I can put this in. This is still an exact answer in my calculator, and it will calculate it however many decimals pi goes in my calculator. So that's why I don't want to round this yet. Next, area of the medium circle, pi r squared. In this case, r is 8, so 64 pi. Area of the small circle, again, radius is half of 5, which is 2.5, and 2.5 squared is 6.25, so 6.25 pi. And lastly, we've got area of the triangle, which is half, 7 times 8.5, which is going to be about 29.75. And now, plugging these all in, we've got 132.25 pi, the whole, minus the 64 pi, minus 6.25 pi, minus 29.75, all over the 132.25 pi to get 0.40. So 0.40 chance that it will land in the shaded area. Next, we've got find the probability that a randomly chosen point in the figure lies in the shaded region. This time our shape is shaded inside, and we've got a triangle isosceles 45, 45, 90 on top of a square on top of a hexagon. Okay, so we need to find area of a triangle, area of a square, area of a hexagon, and area of the whole. 4 pieces again. starting off, we've got area of triangle plus area of square plus area of hexagon over area of circle, and then we're going to solve these one at a time. Starting off with the easiest, it notes that all these congruent one symbol segments are 4, so square is going to be pretty easy. So area of a square is 4 squared, which is 16. Next up, area of the circle is probably pretty easy because we've got diameter down here is 30. So if diameter is 30, half of 30 is 15, pi times 15 squared is 225 pi. Next, a little bit more work down here, as you can see. We've got area of a hexagon. We'll do hexagon first, and we'll do this triangle here. So hexagon, we've got half ANS, and number of sides is 6, side lengths are 4, so we've got that already. We just need to solve for apothem. So down here, solving for apothem, we've got 360 divided by 2 times 6 to find our angle that we need, 2 times n, right? And we get 30 degrees. So this is a 30, 60, 90 right triangle. And then we can use our pattern. That opposite of 30 is my small side is x, opposite of 60 is square root x squared of 3, apothem. And then the big side is 2x. We don't need radius. And we had half of 4 is 2. So this side is 2. Again, why half? Because we're solving this triangle here. We're not solving the whole, just half to make that right triangle. So since x is 2, I just plug 2 into x root 3 to get 2 root 3. Didn't have to do tangent of 30 equals x over 2 over a because we have the 30, 60, 90 pattern. So plugging that in, half of 2 root 3 times 6 times 4 gives you the 2 and the half cancel, so we get 6 and 4 times square root of 3, 24 square root of 3. And then lastly, this triangle up top here is 4, 8, 12 is my hypotenuse, and this is a 45, 45, 90 because it's isosceles right triangle. So x root 2, x, and we're going to do the pattern to solve. So divided by square root of 2 on both sides, rationalizing, multiply by square root of 2 on top and bottom. These will become 2. 12 times square root of 2 over 2. Well, 12 divided by 2 is 6. So that worked to get us both of these base and height are 6 root 2 when you plug it in, and then we can solve. And so that gives us, half of 6 root 2 times 6 root 2. The 2 root 2's become 2 and cancel with that, so we get 36. And now we have all 4 pieces, plugging it in. 36 plus the 16 of the square plus 24 root 3 of the hexagon is the area of the shaded areas divided by 225 pi, and then we get 0.13. Next one. Looking at this might seem daunting. I don't see any values here. How are we supposed to solve? Honestly, if you feel more comfortable with values, it is okay to make up a radius. Just make sure you're consistent. The reason why you don't need one in this picture is because technically we can use, let's just call it radius for now, right? This is radius, and there's 2 radius makes the height and the length or side of the square, right? And so we've got 2r times 2r giving us 4r squared is going to be our area of a square. Sorry to jump ahead, but here's our formula. We've got everything shaded besides half the circle. Why half? It is circles divided into 8 equal pieces, kind of a pinwheel here, so 4 aren't shaded. And so we're just subtracting the 4 8 that aren't shaded from the whole to get the total shaded area over area of the whole. So area of the squared is 2r, 2 radius, squared, which is 4r squared. Area of the circle is just pi r squared, right? We're just calling it r. If you chose radius is 5, this would still work because they would cancel the same way. It would just be easier to plug in your calculator, whereas with this one, we kind of need to do a little bit of the simplifying on our own. So we got 4r squared minus half pi r squared over 4r squared. So these are the same, so technically we can rewrite this as 1 minus this half pi r squared over 4r squared. And now we can simplify, because here the r squared are going to cancel, and now we've got this 1/2 pi over 8 over 4. Well, this half is the same as putting the 2 down here, pi over 8. So when we do the math here and simplify, we get 0.607 is 1 minus half pi over 4, what it simplifies to. Next one. Need an easy one after some of those hard ones. Find the probability of the randomly chosen point is in the figure is in the shaded region. Well, we've got this is an equilateral triangle, and it's cut into 1, 2, 3, 4 triangles. Only one of them has shaded area, so we're going to say 1/4. And now the shaded triangle has 1, 2, 3, 4 triangles as well. And again, I didn't show the congruent marks because it would actually be a big mess, but these are all congruent triangles as well. So 3 of the 4 are shaded. And then we're just going to multiply that. 1/4 times the 3 out of the 4 triangles in the 1/4 gives us 3/16. And that's that. It's actually that simple for that one. Okay. Next, one more. Find the probability that the randomly chosen point in the figure lies in the shaded region of the square. Okay, so in this case, we've got 2 times area of the circle over area squared. Right? So area of the circle, pi r squared, right? Does it get any simpler than that? Area of the square, now this one's a little different, but we got 1, 2, 3, 4 radius here. So that one's also going to be 4 radius. 4 times 4, 16, r times r squared. So we got 16r squared, and now we're plugging it in. 2 pi r squared over 16r squared. Well, 2 and 16 cancel. R squared and r squared cancel. All right? And this would be 8. So we'll get pi over 8 over 2 pi over 16. Either way, and it simplifies to give us 0.393. So pretty close to that 0.40 from the other problem. And that wraps up today's lesson. Feel free to email if you have any questions.